So let's start with this second part of the second day of the tomography tutorial. Before that, I'm going to show you just a little bit, while we allow other people to come. Let me share my screen. Okay. So can you see my screen? Yes, okay. So as Junior said before, and Pablo, all the documentation will be present in Scipion webpage with the user documentation, tutorials. And for example, you have here the one which was made this morning, a little explanation, and then all the slides, links, the video tutorials, and so on. And after that, the recorded session will also be available one way or another. And everything which has been done is explained in full detail here. From my part, the final version is not ready. It is the last before the course. I made some other changes, so I'm going to provide this other link with it's the source code page on GitHub, just to provide you to follow during the course. I'll follow this guide during both the theoretical and the practical parts. Just to, I think it's better to have all of this at site, so we can, for example, concrete the doubts, or maybe provide a better understanding of the reasoning behind one value or another. So the link is on the show notes, but also I'm going. The link you need is it is the same for both sessions, because both are together. Once we are all there, I think it's just to have a quick overview of how it is structured. This is the main the table of contents with everything we have, with the short introduction about Mohammed. Can we also have the completed Scipion projects? They are currently in the remote machines, but also we have on local some the original copy. For example, I have mine in this. I have to think about how we can upload that maybe to our server and then allow them to be available to be downloaded. I have to speak with the team, but I think it would be possible. Yeah. Yeah, I know it's a lot of information, and the most material you have, the other. This is why we are trying to have everything written, and we are recording the sessions and so on. But yeah, I'll talk with the team, and I think there won't be any problem to maybe move them to the remote server in which we have any other things available for being installed with Scipion. Maybe there is some space there where place them and allow you to download it. Okay, we'll discuss about it. I hope there won't be any problem, and I will give you instructions of how to download them and use them. Just a quick, very quick overview, going back to the presentation. This is just to illustrate the one of the main keys of the main keywords regarding Scipion, which is the interoperability. For this tutorial, there are three main plugins, which are the wheel, which JJSoft, with as my partner says before, will be renamed with as Tomo 3D, and the current Tomo 3D will be also renamed. This is due to an agreement with the author of JJSoft to provide a name which is more easy to be identified with his work. But apart from that, apart of JSOF, PySec, and Tomosegment TV, which are the main 3 plugins we're going to use during this tutorial, there are a lot of others which will be also used for intermediate steps or visualization and so on. So indeed, in the end, 9 different plugins will be used for this tutorial. This is like a short menu of what we are going to eat. We're going to import our tomograms. We're going to normalize them just to make them be smaller and make the processing faster. And in this case, it is very recommendable to segment the membranes, because the smaller your the smaller your tomogram is, the better the membranes are determined by the segmentation protocol. And also you can perform some denoising operation to even increase the contrast. So once you have everything segmented and annotated, you can go back to the original size and then move to the picking, where the size is very critical, because we don't want to lose our particles due to any mathematical filtering and so on, which could be, for example, delete them in case they are very small. To finish this introduction, this is an overview of the whole project we're going to carry out during this tutorial. Both parts of the tutorial are contained in this same project, and I used a different color for each plugin, just to illustrate the keyword, the interoperability of Scipion. And I think what the next important point to be defined is what is the objective of this tutorial. This tutorial was designed to pick membrane ribosomes of an in situ tomogram using the membrane segmentation, membrane annotation, and the directional picking tools offered by Scipion, which are in this case Tomosegment and PySec plugins, respectively. The associated resources are a presentation, a small presentation, which is the next point we are going through, a presentation of how PySec works and what it is, which will be at the beginning of the second part of this tutorial carried out, will be presented by Antonio Martinez Sanchez, which is the author of PySec algorithm, and it's a collaborator of our team. And I've also added this link, which explains some basic actions in Scipion for the newcomers. They have been carrying out the day before and this morning, but for example, as you can see, the GUI, how to create a project, how to add in a protocol, everything you have been done in case the time passes, and you can go back here and refresh all this knowledge in case you sometime start to work with your own projects with Scipion. So the data set before going to the presentation is an MDI EMD, sorry, data set, which can be observed here, is in situ tomogram at beam 4 It was the main data set used in the PISEG paper written by Antonio Martinez, and it's available for everyone. So considering all this stuff and with all of this in our things, yeah, in our thoughts. Sorry, I mean, my English is a little bit rusty, and sometimes I forget about some words. I need to fix a little bit my vocabulary. Okay, so we have one only tomogram of intact P19 cells acquired with faceplate with a sampling rate of 30.68 angstroms per voxel and dimensions of about 900, 900, 500, which is beam 4. So with all of this is the scenario of our beginning point. So let me go to the denoising and membrane presentation. And this is my presentation itself. My name is Jorge Jimenez. I'm a software developer in the Scipion team. I studied physics, and so I'm in the midway from algorithms to software developing tasks, but I am full time in Scipion team software developing and integrating packages. So let's begin. Tomogram denoising. Where should I apply it? The main point where tomogram denoising should be applied is after having reconstructed the tomograms. This way we can enhance the contrast, and it can help us to better identify different structures, like in this case membranes or macromolecules and so on. It can be used for the picking, but then we can take advantage on for example, the coordinates picked if denoised tomogram and re-extract them on the original data just to avoid possible mathematical artifacts that, the more mathematical operations you have on the data, the more the probabilities of having some called mathematical artifact, which won't represent a physical entity, it will be more probably to be present. Okay, so this is the rule we're going to follow during this tutorial, and it is very very recommendable to follow it when processing. I'm not an expert in image processing. I'm very far from being like this. This is not my duty, but I try to offer the best practices. I think they are the best. What pros does the tomogram denoising operation? It enhances the contrast, and we've said before, improve the visualization of structure and identification for picking. Possible consequences, as we've said before, we can generate mathematical artifacts, and also if the target particles are very small, they can be removed or filtered. So that takes us to the other question. Is it mandatory? No, it depends on the data set. It is very recommended for the membrane segmentation because the better the membranes are defined, the better they are going to be identified by the segmentation algorithm. It's recommended for a better picking on macromolecules, but recommending after that to use these picked coordinates with the original data, and not recommended when the particles are very small, because they can be, said before, removed or filtered. We have two denoising protocols in Scipion, one from the plugin Scipion JGSoft, which will be called again Tomo 3D, developed by Jose Jesus Fernandez. And the protocol name in this plugin is Denoise Tomogram. It offers the edge enhancing diffusion algorithm and the Beltrami flow algorithm. It can be done using both one or the other, or just both to compare. The other one we have is inside plugin Scipion and CryoEM, which is a whole plugin dedicated to denoising based on deep learning, was developed by Tim Oliver Buchelt, which is also a collaborator, which integrate its own software in Scipion. We helped him a little bit, but he did most of the job, and we're very grateful for that. This protocol this plugin is very good for a very for determining complex structures, cellular surroundings, and so on. But it requires some data preparation to apply it, which is it has a lot of in common with the workflow showed yesterday by Jose Luis Vilas when using Monotomo, because we also needed that even not representation, even not frame representation based to apply CryoEM. This is an example which has been taken directly from the tutorial we're going to go through later. And this is the original in situ tomogram and the result after applying the JGSoft denoiser with the EED algorithm. As you can see, the contrast has been considerably increased. And what else? Once we have this, it's a good moment to go to the membrane segmentation. The membrane segmentation plugin we offer inside Scipion is the CryoEM Tomosegment TV plugin, which was developed by Antonio Martinez Sanchez, which is also the author of PySeg, and by Jose Jesus Fernandez, which is also the author, as I said before, of JGSoft. You can check here the original documentation on their website. The protocol we are going to use is tomogram segmentation inside that plugin. And it's based on three main points, which are a Gaussian-like model of the membrane profile, a local differential structure approach, and an isotropic propagation of the local structural information using the tensor voting algorithm. A lot of very complex stuff and words, but we'll see in an example where have tried to offer a conceptual idea of how to interpret all these parameters and so on. We'll see later. So, Tomosegment TV carries a lot of operations when it's executing. There are 5 steps, which are these ones. The next slides explains a little bit in what consists each of these steps and what is the Scipion protocol parameter involved. So let's go back. Let's stop here. Let's begin the practice until this point, and after that, we'll carry out this operation together and we'll discuss the different intermediate and final results obtained. So let's go to our machines. I haven't started mine, so if you haven't, I suggest you to do that. Okay. let's create a new project, which will be called. You can call it as you want. I will use day2 R2 in a very original way of thinking. Okay, I'll put this tomography protocols here, and let's start the dataset. Let's start importing the tomogram. Yeah, maybe it's easier for me. Okay, so files directory is the data day2. As we have said before, the dataset which has been directly downloaded from the EMDB. We have also transformed the original map format into MRC just to skip this step inside Scipion, but no worries about this. We're going to cover it inside the code in a future release. So let's select this. We can add the path with a file in case there is only one file, or the path and the pattern, as you have said, we have said, and you can also have done during the previous sessions. If you remember, the tutorial is telling us, I don't know where I put it. Okay, let me go back because I would like to all the time relate one thing and another, just to be the closest possible to the way when you are alone and you are going to try this in the future. Okay. Let's see. Oh, okay. So no worries. I'll go back there. So here, as you can see, you can go to the main page where everything is explained. Here it is a little bit resumed. So we have 30.68 sampling rate. 30.68. The path is very home Scipion data day2 EMDB score minus 10439. And if you directly double click on it, double click maybe displays it to you, select it and click on accept, you will have all of this. Let me execute this.
When you put the sampling rate, the dots button did not work because the numpad does not work with the Novian C.
Oh, sorry, because my I don't know why it didn't take it. Very many thanks, Mohammed. Let me
You're
restart
welcome.
this. Yeah, my keyboard dot, at least the numerical keyboard didn't work properly. Now it is fine. Okay, many thanks. So as you can see, with iMod viewer, I'm going to be a little bit fast with these steps because I'm considering that you are now familiarized with them. It's thicker than it needs to be, but this is what we have in this EMDB entrance. So I expected these machines to be faster, but it doesn't matter because it's only the 3D view of the image we have observed before here, which is basically this. You have all of this here. In case you get a little bit lost, maybe you can directly, everything is written, but you can directly look at the pictures, what I have to do to create it, what patterns or what needs to be filled here and how it should look like after all the operations. So, come on. Whew, we are almost there. I don't know. Okay, because it was opening before due to my double click. So, as you can see, move it manually. It is our tomogram with a lot of vesicles, and we have isolated ribosomes, and we have in some of the membranes some ribosomes which may be bonded to them. Bonded. Let me check the chat. Okay. So this is the data we're working with. The next operation, very, very fast, is the tomo normalization. As said before, just to make it be smaller, we'll search for IMOD, tomo normalization, and we're going to divide by 2 its size. This is the pointer to the tomogram we have already imported, and then just with only these 2 parameters, click on execute. And as said before, you can see everything is again, all the reasoning and so on is written here. Again, where to look for the pointer, which do we have to select, and how, which other parameter, and just after that, pressing the execute button. Binning 2, yeah, that's correct, Tamara. So in the end, our tomogram is half of the size as it was before. As you can see, the sampling rate has been multiplied by 2. Now, all, yeah, so the IMOD viewer, I don't know, because the tomogram is thick, but it's not as big as I don't consider it to be so big, but in these machines, some things are a little bit slow. Yeah, I completely agree. I agree completely with you, Bram. The normalization step. I also agree with you. Yeah, I'm not sure about the hard disk of these machines, but I'm afraid that maybe it's not an SSD. So the grading and reading velocity is not maybe as fast as we are used to. Oh, me. Okay. For a third time, I agree with you, Bram. Okay. So, the first step, which is new in this tutorial, is the denoising tomogram. So, as you can see, you can follow the guide. Go for it, JSoft. We have the Denoise tomogram protocol. We have pre-selected the algorithm we are going to use, the EED, and then we have to select the normalized tomogram. Just execute, leave the rest of parameters be like this, with the default values. Okay, thank you, Paulo, for helping Francisco.
Jorge?
Yes, Maria Jose?
Yeah. Could you go slower and repeat the last step, please?
The denoise.
Yes, thank you.
Sure. Yeah. To look for it, just click on Control F. Let me Control F, or it can be located here somewhere. But I'm used. Let me do this that way because I'm used to do that way. I'm very slow when I try to look for them. So you can use some keyword, for example, in this case, the current name of the plugin, which is JJSoft. Double click on the Denoise tomogram protocol, and we only have to select the set of tomograms pointer, which is we have to point to the normalized tomograms. By making them slower, the next calculations will be faster, the membranes will be better defined, and with the denoising will be even better defined. The rest of the parameters can be left with the default value, and the result I'm not going to open. Well, yeah, because now it's smaller. Let's give another chance. Oh, nice. Smaller, small things are always faster. So this is our denoised and normalized tomogram. As you can see, the contrast is much more better, and it's much thicker than it needs to be. And as you can see here, we can observe all the structures and our ribosomes, which are bonded to some vesicles. So, what else? What's the next step? Next step is to segment the membranes. And we're going to go through this together with the theory. So, Control F, segment TV, and let's select tomogram segmentation. Double click on it, and let's place the following parameters, and while it's running, we're going to talk a little bit about them. So let's point to our denoised tomogram here. We are going, in this case, to leave this membrane thickness parameter to 1 voxel. Then we'll discuss why. This is not exactly membrane thickness. It's a filter which should be of it, but if you know a little bit how it works, and it's very well explained here, and it's also explained in the documentation, we're going to talk a little bit. And the membrane scale factor, it will be 8 voxels. Again, we're going to talk about this later. Our image is black over white. And if you click on Advanced, other parameters which are going to be used, not always, but in this case, they are going to be. First of all, let's update this parameter to 0.01, which is a parameter called membrane strength threshold, and the sigma for the initial Gaussian filtering to 0.5. Finally, let's update to yes the all generated files and execute. It shouldn't take so long. So, what's
Okay,
here?
I think you did the same mistake again. You put 0.5 instead of 0.5.
You are like my angel, Mohammed.
You are welcome.
Yeah, because I'm used to use my numerical keyboard part, but it's not working on the remote machine. So maybe I do this mistake some more times again.
Could you please
Okay,
explain?
now it seems to be working fine. Many thanks again, Mohammed.
Could you please again explain about the noising step? Is it just Gaussian blur applied to the images just to see them better?
It is using the edge enhancing diffusion algorithm in this case, which I have been familiarized sometimes with it. I have to read sometime about it, and I think that Jose Luis Vilas explained yesterday and Federico. Let me continue, and during the break we can go back and explain with it, maybe with Jose Luis and Federico, to go through the theoretical details, if you don't mind. Is it okay? Let me check it out. Doggy. I have here another window. Yeah. Okay. Thanks, Dimitri. Okay, so these are everything we have been done when updating the parameters. And for example, one good question. Why is the membrane thickness set to 1 voxel? If you are segmenting membranes, it's a good strategy because we are going to we prefer to go to an scenario in which we have over detection that then can be corrected later, instead of the opposite scenario in which the membranes are not very well detected, and then it is very difficult to annotate them properly for the PISEG calculations, which will be carried out later. This is the reason we are going to use this filter with 1 voxel thickness, just to provoke over detection of the membranes. The membrane scale is 8 voxels. This is to define more or less the effective neighborhood, which is the surroundings around this 1 voxel line considered for the calculations, which means that to consider if we are in a maximum or a minimum situation when we're calculating, we cannot consider just a 1 voxel line. We have to consider a little bit of the surroundings. We need that information to determine if it's comporting like this, like a flattened one, like a minima, and so on. So more or less you can calculate, considering the pixel size and the size of the particles we are going to try to detect, what values should it have to have. In this case, the only things that matters is that you are able to get all the membrane and a little bit of the surroundings without considering the particles in this case, to determine its behavior when it's calculating. And the other critical parameter is the membrane strength threshold. This parameter is very important because it can be used to more or less conceptually determine the sensitiveness of our algorithm when detecting the membranes. A very low value means which we are going to pick a lot of points, connected points, which will be considered membrane. This is a bad situation because if we have this scenario, then if we want to separate one vesicle from another and they are detected as connected elements, then we cannot annotate them properly as different elements. On the other hand, if the value is too high, we can have discontinuities in our membranes, which may take us to lose some information and to make more difficult the annotation procedure. So this is just for refinement, the Gaussian processing, just to make the edges be a little bit sharper. And with all of this information, sorry if it's a little bit complex, but in the end, once you read this in detail, slowly, and considering this, we are going to purely relate it, but we are going to do it in a reversal way. So let me go back to the machine and show you. We have a tomomask. A tomomask is a representation, a segmented representation of a volume. In this case, it is a segmented representation of our volume. So why I told you to put to yes the parameter keypole files? because by default it only stores the final result, which is this file. But this kind of algorithms, do you have to fine-tune the parameters. You can determine them by reading them, understanding them, and adapting them to the data set you are working with. But sometimes they have to be refined, and the only way to do that is observing the results and some tries that take us to the best result. I recommend you to do that with a small set of your data, even one tomogram. Once you have the parameters fine-tuned, then apply them to all the set. So we can open each of them, of these results, just to go through them. So let's go. I'm going to go from the last part to the first part. These are the results we have. This is our original data. This is the first step, which is called scale space. This is the second step, which is called the tensor voting. Third step, which is called the surfaceness. Second, tensor voting, and saliency. Why I show you this? Because, for example, imagine that our result is a black box. At one of these points, something is messing up. So if you understand what represents each of these intermediate results and which parameter is the main one related to each of these steps, you know better how to find the problem and how to fine-tune it. So, scale space, what does it do? It allows isolation of the information according to the spatial scales by a Gaussian filtering out features with the size smaller than the given scale. So, we're now applying a Gaussian filter just to determine sizes in terms of the thickness of that filter. The protocol parameter involved is the membrane thickness, the one we have put to 1 voxel. The one. It's very difficult to lose all the information here, but it's better to know everything. After that, we have the second image, which is this one, the first critical point, the first tensor voting. The first tensor voting consists on check the surroundings of the voxels by propagating the information from one to another. This is like an object detection technique. Considering the surrounding of each voxel, the properties are updated and refined, and then you try to define how it behaves from one part to another. What is the aim of this step? The aim of this step is to enhance the membranous structures. And the parameter involved is the membrane scale factor. So what I've said here is go from the first umbilical line inside the membrane of 1 voxel thickness, goes both sides of this a thickness of 8, and then use this information to determine if it's a membrane, if it's this shape, if it's flat, and so on. Then, I have too many things open here. The third one is the saliency. The saliency is used just to refine. So once we have this, we can refine them in the saliency, surfaceness, sorry, in the surfaceness, which makes eigenvalue Hessian tensor, very, very nice to tell here, suited to determine the normal direction and provide the membrane strength of each voxel. What does this mean? What it means is that we are applying some kind of mathematical operations to provide a value called membrane strength to each voxel. This value will be used later to filter this volume. So this is why a very small value will consider a lot of points and connections, and a very high value will take into the scenario of having a lot of discontinuities. So apart from all of this mathematical stuff which has been added here, because I think it's necessary to have it here, the aim is to provide a membrane delineation, to know its normal direction, and to provide them a value which will be used to be later filtered. So if and up to this point we have all our membranes, we're in a very good situation, because the second tensor voting is just like a refining step just to fill the potential gaps and increase this robustness of the surfaceness map. It's like a refinement of the previous result. But here it is the other parameters. So let me go back again, because maybe it's getting a little bit messy. Here, for the surfaceness, we have this membrane strength threshold, which I am telling it you are assigning one value to each voxel. You have been considering that it's a part of a membrane, and to filter them and consider which one of them is connected to another, I'm gonna tell you what value you should use. These values can be from the default poly, a little bit smaller, a bit larger, but always having in mind that lower values will provide more connections. Higher values will provide less connections. So we have to go and pick a value which provides enough connection to have the membranes as complete as possible, but not being over-connected. And for the second tensor voting round, again, is the same of the same parameter that was used for the first one, which is this one, just to tell them again which surroundings have to be considered. Finally, for the saliency, it is again, for the saliency, it is again the same. Is the surfaceness applied with a small different behavior inside the algorithm. We are a second delineation after the second round of tensor voting, and here the sigmas, the final parameters here. I think I have too many things here. No, it's okay. These sigmas are the ones used for provide a better delineation of the membrane edges. You can, in the tutorial or even here, read a little bit more in detail, because I think I'm taking too long here. So, in the end, this is the tomogram. How should we use it? Just the same as in the documentation, and a small table about which step, which file name generated, if you click on keep all generated files, corresponds to each of the steps explained before. So all of them which will have the same file base name of the input set of tomograms, once for each, and with different suffixes. And this is the final result. A good result is this one, which you can see very, very low noise, and the membrane is very, very, very thin. So more or less like the umbilical line, which is the best scenario which can be offered to the annotation step. And then just always I have to thank to all the team, our partners, our collaborators, which have been working very, 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 very hard during all this time, and our funders. I always want to remark this because a lot of people and a lot of funding is behind all of this work. So many thanks to all of you. So at this point, we're going to play a little bit with the membrane annotator tool. So,
Jorge,
yeah.
Bram is asking about the parameter to adapt a thicker membrane.
A thicker membrane would need this parameter to be a little bit higher. You have to make a small calculation about considering your sampling rate and the thickness of your membrane to ensure here that you cover the whole membrane and a little bit of the surroundings. And the other case would be this one, but this one is more related to the sensitiveness. So this would be the two parameters. This one would be higher, and this one, it would depend a little bit on your data set. I would use a higher value because as the thicker the membranes are, most probable that you are going to go to an over detection scenario. So you can try higher values, for example 0.3, which I think it's the default one, and you can observe the result, and then from that, knowing the things we have been mentioning before, you can adapt the value of the parameter. Yeah, membrane strength should be, yeah. This has the membrane strength threshold is doesn't have units. It's just a threshold, like an intensity value. I don't know how to. It's the result of a calculation. Maybe it has some kind of units. I'm not sure about it, but consider it like in a 2D image at the intensity value, for example, and then if you are trying to binarize it, you fix a threshold in the grayscale to tell it what has to be black and what has to be white. It is the same idea. Yes, I was going to go later with it. The membrane is about, we have considered this membrane to be 60 Armstrong because they usually are of 40 Armstrongs width, but someone which is more wiser than me told me that if I consider the heads of the phospholipids, I don't know if I'm correct I'm pronouncing them properly, it can be of about 60, so about more or less. But with this pixel size, doesn't represent a very good, a very high difference. We'll later this parameter will be critical, so and we'll discuss a little bit about it. Meanwhile, let me just to have enough time to play with this fantastic tool. Let me annotate, for example, and click on Tomo Segment TV, annotate segmented membranes. This protocol is very, very simple. You only have, it's an interactive one. Hope it works fine for all. You're ready to play. Double click on it and then execute. It takes a little bit because it is Oh, okay. Double click again here, and it seems to be doing nothing, but it's not. It's not real. If you click here on the output log, you can see that it's running the memory annotator and it's loading. I'm planning to put a splash window for this to explain it and not to cause the impression that it is frozen. But meanwhile, it takes a little bit to load because it is written in MATLAB and it has to load some libraries and so on. So while it's loading, let me go back here. Yeah, this is the steps we have been carrying out. And this is an over. Yep.
I don't understand why we are using the annotate segmentation. This.
The annotate segmentation is used to select the membranes we desire to be working with for the picking. So here we will consider only the membranes which have or seems to have ribosomes bonded to them. This way we are going to annotate them and then cut them to only work with these subvolumes, with being a vesicle each subvolume for the picking.
Okay, and which is the path to run them?
Yes, it's just let me go back here. Just click on the magnifier icon and select the result of the Tomo segmentation step carried out before. Then click on execute. An auxiliary window will appear. We only have one tomogram. If we have more than one, all of them will be listed here, and it is telling you which of them have been annotated and which haven't. Just for your information. And once all of them are annotated, it automatically generates the output. So double click on the only one we have, and after some seconds, the membrane annotator tool will be opened. Everything okay?
Okay. Yeah, perfect.
Okay.
Thank you.
Cool. Thanks to you. Okay, so this is how it looks like. Here you have in the manual, just to go, when you look at all of this information slower on your own and so on, a very full detailed user's guide about which element and the utility of each component of the user interface. Everything is explained here. And I'm going to move forward a little bit just before going back to play with it. I've chosen for this example these three vesicles, which will be referred with these indices in the documentation from now on. Because these are the ones which I've considered them to be the best candidates to have the higher number of ribosomes bonded to them. In other cases, I've tried to annotate more of them, smaller ones, just to try to have a little bit a higher set of particles. But for this tutorial, I think these three ones have most of them. So this is our target, which would be from here chosen after if we haven't observed this data in detail before, we can do here. We can move the slices here and observe in detail the changes from one slice to another, considering how the shape changes and if the ribosomes appear or not. They can be also fine-tuned from here, introducing the value and pressing the intro. The first step we have to carry out here is the density thresholding. This is like an enhanced operation of the tomosegment TV algorithm, but dynamically. As you can observe, the result of moving it is to move this kind of membrane strength parameter to observe more or less connectivity and structures here. This way, when we have a good result, which means I am able to observe most of the vesicles clean and low noise and small structures in the background, I can go, let me check in the documentation the best value for it. Okay. 0.05. This is the best value. Okay. It wasn't prepared, but you know. Okay, the second step is to go to this panel. Let me explain a little bit this. This panel is just to change from the original view to the threshold view, the filter view, the label view, which will be generated later, and the material view, which is the selected vesicles with the index we have been used to annotate them. This is a cropping panel. For example, if you want to avoid some strange structure on your tomogram and you are going to work with the full tomogram, you can cut it using this X, Y, and Z coordinates and clicking on update. But we are going directly to the size threshold. All of this is explained in the documentation. Click on update labels and wait for a little bit. This operation is checking the connection of one structure to another, and it assigns a different color, which means a different size, to each of them. So, what's the correct usage of it? Let me show you a little bit how does it work. For example, let's focus now on this first vesicle, which is one of the best candidates. What we observe is that, if you can see here, the index is the value which has been automatically assigned and represents the voxels of this structure. So different values mean different structures. But if we know that different structures are for real the same structure, we can annotate them with the same index. The problem, for example, could be with a very low value of the threshold, and this could be annotated, automatically detected as the same structure. This way, we couldn't be able to separate them, annotate them as separated structures. So as you can see here, this one has a different value than this one. This one and this one are this. These other parts are again this. And this part is a little bit different, which makes correct the value. So we have here all this orange have the same value, which is the same structure. All of this has been identified and a different structure, and this is another structure. Since we are now focusing on this one, we are going to annotate first this and this as the same. Yeah, this is what I'm going to how I'm going to go through this. Okay, this is just to provide a better understanding of the tool. So you have in the size threshold panel used before to update labels, you can display cursor to select one structure. Okay, you can move it with the keys and check the value. Once you have finished, you can stop cursor. You can add other cursors with right click, create a new data type, for example here, and place. so you can have a full overview. I recommend to use these tools with the click and drag functionality, just to be focused on the region of interest and use here these values. So once I have finished to measure the size of the different structures, and I'm sure what I'm going to annotate, which are in this case this and this as this vesicle, we move to the display cursor. If there are a lot of noise, even if the threshold value here takes you to an scenario in which small things are here bothering and getting and making your structures dirtier, you can measure the sizes and use the size threshold button to remove them. So I'm going to annotate this one with label 1. So label 1 is currently here. Let me annotate this. Be sure that you are in an index which is different than 0, because 0 is the value of the background. You can fine-tune or make a higher zoom with the clicking here and with the mouse wheel. And everything which has value 20, 100, 90, and 74 will be now annotated as 1. So I click again on change label. And something messed up. Okay, so cool. Okay, something has broken. Let me. Why? It's been broken. No, label. Annotate. Let me go back. Okay, I think there has been a problem with the cursor. No. I think I have messed something while I was checking. Let me reboot it. So, you know. I know what I did, but I lost the cursor. Maybe I was touching wherever I shouldn't do. I don't know, but no worries about that. So, like, oh yeah, Mohammed, no. Okay, update labels again. Yep. Let me go very fast here. This is the point in which we were before. I think I didn't stop the cursor, because you can display a cursor, check something, stop cursor, and then everything goes good. I think I have mixed the cursors. Be you're cool, Mohammed. And then let me annotate this. Okay, this one with this value will be annotated. Yes. Woo! Now in the material view, we can observe that this structure has been almost annotated. If I go back to the label, and now that I am sure that it won't be connected with any other thing, strangely, I can now use the same label to display the cursor, click here, and assign by clicking on change label the same value, which is 1. Oh yeah, we have, this is it is not the whole membrane, but it is the best we can have in this case. But a lot of information can be obtained from there. This is a not easy case. How do I get there now? Okay, let me, Tamara, I'm going to annotate.
I think I used also the wrong cursor because I'm not able to do the labeling and to get this nice background and stuff.
Okay. Okay. So I think the best way is to reboot again. So to do that, just in the close all the other windows, the related, the other ones related to the annotator and so on. And with this selected, click on stop and yes. Then it will be painted in red and the status will be failed. Then you can double click or right click and edit, click on restart, which will restart the protocol and execute. So far so good?
Yes, we are following.
Okay. So I'm going to annotate the second and the third vesicles, and the procedure is the same. So let's try to do them together. And if you get lost, we have a little time to have all of this ready. So once here, just as a quick resume, we have to place the value 0.05.
Mine is not restarting.
Let it. Maybe it after the double click on the tomogram list, it takes some seconds to display. If not, maybe.
So I'm asked whether I will want to restart the workflow.
Okay, Patricia is going to connect to your machine and is going to help you.
Okay, thank you.
That. Thanks to you. Okay, so with this value of 0.05, I'm clicking OK on the intro key. Then you will be moved to this view, which is the threshold view. Then if you click to update view, you will be moved to the labeled, the automatic size assigned to the different structures. And we can discuss about the in the target vesicles about the sizes with the display cursor and then stop cursor. We'll try to make this tool be better and not more robust in case of the when it's in the cursors. And at this point, I'm going to do the second one. The second one was this one. The top colors seems to be present here. What I want is this one. I don't want this to be identified with this, of this, or this. This is clearly different. But let's have a look. What I have here is this value. Let me create a new data dip for this, which has a different value, and a new one for this. I'm going to create a new one even for this. So as you can see, this has one value and this has another value. Perfect, we can annotate it. And the most important thing is that this structure is different than this, and this structure is different than this and this. So we are perfectly at the point we need. So I click here on the set material display cursor. I'll call it material 2 and I change label. I don't believe it. Something is getting messed with all these data tips. Let me try to check it. No, it is dying. Another cursor is activated. I don't know why it is failing, because I did when I did it. Yeah. If I use these cursors, I don't know how to pronounce. I'll have a look at this. Yeah. I'm feeling tomatoes being thrown at me. Okay, let me redo again. So another resume for all the people here. I apologize about this because I haven't found, believe it or not, these problems before. I don't know why. I'll have a look, and software will be updated when it's solved. So let's restart again. Sorry for the inconvenience, my fault. And the sizes will be, let's check them directly on the documentation until my problem with the cursors is solved. So I'm going to do it in loud voice. The threshold should be in 0.05. Oh, Mohamed, I'm feeling you so far. Yeah, now. Then in the size threshold panel, you just have to click on update labels. And then we are going to directly annotate them. We have all the discussion of the sizes. We all have checked out that everything is as expected. And we are going to annotate this, change label with label 1. Let me go back. Label view, magnifier, this structure, display cursor. Here, the same label and change label. Nice. I go back again to the label view. Let's go back to the second vesicle and let's follow the same strategy. For this part, let me annotate label 2 and change label. Okay. As you can see, we have the higher part of this vesicle. I go back again to the label view, use the magnifier again, and annotate the lower part of the vesicle with the same label, in this case, label 2. Let's display the cursor, place it here, and change label. As you can see now, you have the first one and the second one. Membranes, quite well annotated. And the third one is the easiest one. I've keep it for the last. Yeah, this is very almost completely continuous. Even in some of these slices, it seems to be completely continuous structure. So we display cursor, add this here, update the label to label 3, change label, and this is the final view we should have here. Let me finish this, and we can solve together everyone who has got stuck here while this is a break time, but we can continue if you want. The ones who has reached this point, just now click on Save Materials. Save Labels is used to store the values of the automatic calculation that carried out with update labels value. This is not used in this tutorial. It can be used for whole tomograms, annotation, and so on, which aren't in the scope of this tutorial. So you have to click on Materials. Then here in the log, you can observe materials were currently saved. At this point, you can close it. And this pending window will change into done. Then you can close this. And let me refresh this. Okay. Now I have finished. I have all segmentations annotated, and I have a set of tomomasks, which can also be visualized with the Tomo 3D viewer. Wait. While it is loading. Okay, so yeah, the index is 0 when you are clicking on the background. You can perform small movements of the cursor with the arrow keys in your from your keyboard. Anyone who is stuck in this part and needs help to have it ready? Yeah. Okay, Bram. Okay. All I don't know if in the external. No one is in the external. Okay, so I can connect to one of the machines of you, and I can repeat the whole procedure, and you can follow me.
We can do it, Jorge, if you want.
As you wish. Okay, we will continue here if no one is in the other. I don't know if I am working this correctly.
Other possibility is to repeat this step here again, slowly, just to pick or to remind the process.
Yeah, could be. Okay, I'll let this.
It's Luca. I am stuck always at the place cursor phase.
Okay,
so if we repeat from the scratch, it would be useful.
Okay. I'm going to repeat this. Let me.
Okay. Thanks.
Let me make a copy. I'm going to make a copy on this machine and execute it. And we'll do it again from the beginning.
Can we maybe confirm to you if we can follow you? So if the same step works also for us?
Sure. We're going to carry it out slowly because it's break time. Anyone who has reached the final point can go there, and the ones who not, please stay here with me, and we'll try to do it. And if not, we can take the result from the whole project. But I would like to have all of this done. Okay, I haven't double click. Okay.
I'm now waiting in the membrane annotator with a threshold of 0.05, but everything is black when I put label or threshold now. So black and white.
Okay, try to update. Move for example, click here from the threshold now is, I don't know, maybe it's being interpreted as 0, or maybe you have the same problem with me with the numerical.
I used a point. So okay. it's written here 0.05.
Okay, got it. So then are we all here in the 0.05 thresholding? Yeah, nice. Okay, good start, Dimitri. You're great, man. Okay, nice. Okay. So now let's click on update labels to make the algorithm calculate the size of each separate structure. And we would have this representation of in different colors of the different independent shapes that have been detected. Okay. Now To try to annotate it.
Please, one question quickly.
Yeah.
So, is it normal that if for the same Z slice as you, I see different features, slightly different features, let's say different volumes?
Are you in the same slide, set slice?
Yeah, I think so. 125,005, and the coordinates.
Maybe it was some different parameter, for example, in the sigma in the previous data. But let's continue, and because maybe the values are a little bit different, but you get the final annotated structure the same as the rest. Let's try. If not, just tell me and we'll solve it. Okay, so click on the magnifier, click and drag here, for example, just to be sure that this or this is present, and then click in Set Material panel in Display Cursor. Let's click on the orange structure here. Be sure that this is a value different from 0 because it's not you were annotating the background, and click on Change Label. At this point, you should have to be visualizing this. Yeah, I'm very sorry about the problems. Maybe I'm very used to use this tool, and I don't know, but I'm not familiar with this stack. I didn't find them when I prepared the documentation, but we'll work on it and we'll solve it to provide you the best experience. Okay, let's go. So let's click now in the label view again. Let's click again on our magnifier and annotate the top part of the first vesicle with the same label 1. So let's go again to the Set Material panel, Display Cursor, click here, be sure that it is different from 0, and Change Label. And we should have this. Sarah, I see you are laughing. I hope your happiness laughs. Okay. Nice to read it. Whoa. Okay, this is what I like. So let's go for a second one. Okay, so let's go back to the label view again, to the magnifier view, and select the second vesicle. Once here that we are sure that everything about the sizes is correct, let's first update the label to value 2. Click on Display Cursor and select, for example, the top part of the vesicle. I've clicked in 0. I am using the keyboard arrows to move it. Now I'm sure that I'm clicking on the right place and click on Change Label button in Set Material panel. And really nice. Everything's fine. So far, so good. Oh yeah, I love you all. Oh, Luca. Okay, we can. Jordi, how different? We can have a look. Maybe Patricia or Ana Vilas, can someone of you connect to Luca's machine and check if the volumes are well enough to continue? Okay, I'm going. Let's finish this task. We're almost there. Okay, I go back to label view again, magnifier again. Let's select the second target vesicle. The label of the material is in value 2. Then click on Display Label button. Let's annotate the lower part of the vesicle and click again on Change Label. And now 2 of 3, close to the end. Everything is fine until here? Oh, yeah. Yeah. Really, really glad to read it. So the easiest one, this is one. Let's go to the third one. Again, once you have familiarized with the tool, it's very, very easy. Just once you have in your mind the sizes and so on, it's just the same all the time. So let's go back to value, click on the magnifier. Remember, this is the third vesicle we're going to work with. Let's update the label to label 3. Let's display cursor. Let's click on the membrane. Be sure that the value is correct, which means different from 0. And let's click again on Change Label. If you are here, click on Save Materials, run, and don't look back. Okay, it's not the WhatsApp flamenca here, but I have received it from you. Okay. So once you have completely sure that the materials were correctly saved, you can close this window. And after a very small amount of time, it will be updated to done. Then you can close this window. And if you are a little bit impatient, just like me, click on refresh, and you would have this. And if you want to see something fancy, the result of your hard work in a very fancy view, you can display the slice mode and the vesicles. And oh, I think my machine didn't like this. Okay, vesicles, let them to render. No, Tamara, can you click on refresh button here? If the remains in pending state, just let's make a small check-in. Click on browse. What's this? Click on browse, extra, and you should have to have this here. If you have this here, it means that everything is fine, but that window didn't refresh correctly, so you can cross your fingers and close it. Everything should be fine.
It doesn't change anything when I click refresh.
Have you tried this? Have you checked that these files are present here in this directory? Let me repeat it again. You have to select your protocol, click on browse, click on extra, and you should have those files there.
No.
Oh, did you click on Save Materials?
No.
Did you close the
Yes.
No. No worries.
Sorry.
No worries. Everything's fine. I think I'm not sure my partners were Yeah. Can someone connect to Tamara's machine and open?
I was so happy that everything worked that I forgot to press save.
No worries, no worries. For the next code revision, I will add some functionality to ask you before going out of before closing if you are sure. Maybe it's necessary. Not to you because it happens to me a lot of times. So I think it's necessary. I'll do it. My recommendation from now is you. Okay, I can. The rest of the people, are you more or less all right? Bran likes the fancy viewer. Okay, fancy viewer is just selecting the protocol and click on analyze results. And then double click on the first element. You can click on vesicles, let them to renderize. If it takes too long, do not worry about this. You can have all the explanations here and the view of the fancy viewer. Okay, now you can play with this. Meanwhile, let me for Tamara, and if some of you have problems, I'm so sorry to read that, Tanya. Sorry. Okay, so for the ones who has problem, okay, and then I'm taking too long. Just very fast. Let me. You should go to the projects list you have been observing. It is the first window displayed when you double click on Scipion icon and open project day 2 picking memseg and piseg. If you click here, you have the version of the whole project. And I suggest you to continue from here. This is the point we are right now. And you can continue from here just by, for example, then we are going to resize it. What I suggest you to do is just copy the box. It has directly the input values updated and execute. Then you can be executing this by making copies of what is done. You don't have to look for the protocols, but you are enough familiarized to do it. And that way we can walk around the problem of the non-saving issue, because and I promise you to make it better and ask for all the people which is trying to close this if it's everyone is sure and the materials have been saved. And I see a flamenca. Okay, so so far so good until here.
Yeah, I just duplicated now, and now I have a finished resize segment in this document.
Okay. Everything was very well done by you, Tamara. The problem is maybe I should have emphasized more in the critical point of Scipion. But we can have a walk around and continue from there, like a checkpoint.